Hello class, in our second video on Unit T, we are taking a look at three different tests here which you're not going to have to do by hand. And you also won't have to do them by computer unless they are on an assignment or in your big project. So it's still worth going over them here. And also you should know the differences between them all. So in this particular one, we're talking about tests and confidence intervals for the difference of means, independent samples, which is basically given in almost all of them. Population variances are unknown, so that means that we're talking about a t-distribution, but the variances are equal. Now, here's the thing to note about this, is that this comes out to be the same in terms of results as if you were to do this as an ANOVA. So in an ANOVA, you would be doing this as that mu1 is equal to mu2 against the alternative that at least one differs, or in this case, of course, since you only have two, that they differ from each other. And if the variances are equal, then actually the results that you end up with from ANOVA are exactly the same as you get from a T. So why would you use an ANOVA over a T? Well, because the ANOVA template, it's called ANOVA template, right? Dot XLSX, that's that Excel formula template that when you stick the data in there, then you can turn to the Bartlett's test and you would find out whether the variances are equal or not. Now, of course, normality still has to hold for all of these, so you would first turn to the Anderson-Darling section and look at the normality tests, and then if they hold, you look at the Bartlett's test, and then if the Bartlett's test holds that you do not reject HO, then actually your ANOVA results will give you exactly the same p-value as you get if you were to use this particular test here. So that's an interesting thing to note here. And what that means then is that practically you won't need to do this, because in order to find out whether the variances are equal, I suppose you could do an F test, which you learned about at the beginning of Unit A, but you might as well use the ANOVA template, and the Bartlett's test will tell you the results there, and then you've got the ANOVA output anyways. So you're not going to have to do this by hand, and in fact, even on computer, you can just use the ANOVA results if you end up with equal variances. But I do want to just take you through this to show you how this thing works. So this is just more informational. It's a T statistic here. And so we've got a differences of means here. And of course, mu1 minus mu2 is going to be equal to 0. We're going to test the hypothesis that they're equal or that they're not equal. And so equal means that the difference is equal to 0. And then what we've got down here is actually an SP squared. It's a pooled standard deviation. And if you take a look at that, that looks an awful lot like SSW over NT minus 1 times 1 over NA plus 1 over NB. Well, at least it does to me. And in fact, it turns out that it is when you're dealing with just two treatments here. So this is how you calculate the pooled standard deviation using that. And this follows a t-distribution with the degrees of freedom are n1 plus n2 minus 2. And then here's the confidence interval that is down here. So I just want to take you through an example here. I already got the thing all written out here. And if you want to try this on your own, what you can do is you can certainly stop the video and take a look at this in more detail. But let me just really quickly walk you through this. So considering the Stats 101 data, see if there's a difference in Math 30 marks between old students, 25 or older, or young, and assume that the population variances are equal here. So Bartlett's test then tells us that they are equal. So here's your sample means, and then here's your sample sizes right here. Those are the n's, and then here's the sample s's right there. So just going down here, what we've got is, I'm assuming an alpha 5% for all of these. The null hypothesis that the means are equal against the alternative that they're not. Of course, that could be one-sided if the problem was worded differently. This is a T statistic. And then this is a, of course, it's a two-sided test. So what we're going to do is we're going to use a t-distribution. We had 100 observations, so 100 minus 2 is equal to 98. And so your critical values are plus and minus 1.99. Up here we've got the calculation of the pooled standard deviation. And I'm not going to walk through that with you, but you end up with a pooled standard deviation. Sorry, a pooled variance, because it's SP squared, of 217.204. And then you stick that into the formula here, and you get 1.50. And 1.50 is not greater than 1.99, so do not reject HO. Now, if you were to do this, before we get to the Excel output, let's just take a look at the confidence interval here. So the confidence interval then is just the differences in the sample means plus or minus your t statistic. Remember, this is all one number, and it's the 1.99 here. And then these guys, which also appear above there. And so we get the difference in means is 4.56 plus or minus a margin of error of 6.042. And that gives us a confidence interval that looks like this. What I want you to notice is when we were talking about the multiple comparison of means in ANOVA, remember we were looking at the difference of means. And if you have a negative lower bound and a positive upper bound, then it means that that interval contains 0. And that means that there's no significant difference between them, which is what we've got up here. We do not reject HO, and so we conclude that the two are equal. All right, in terms of the output here, so if you were to do this using a t-distribution, as I mentioned, you don't need to do this if you have ANOVA here and the means turn out to be equal. But this should give us the same results in terms of a p-value. So this is a t-test 2 sample assuming equal variances. And so what we've got down here in the output is, here's your first sample, here's your second sample. Now what I've done is I've unstacked the, just like you would do in ANOVA, you unstack the variable in terms of the age categories, old and young. So what was the variable here? Oh, math 30 marks. So that was your interval variable. And then your nominal variable here then is your age class classified as either old or young. So we've got the old column, and you've got all the ages, and then you've got the young column, and you've got the ages here. And there's 38 of these and 62 of those. Now, by the way, we had 38 and 62 in the last example. That's just by coincidence. The old people are not the smokers, and the young people are not the non-smokers. They're completely different. It's just they turned out to be the same numbers. That's all in the last video. Okay, but back down here then, continuing on, we've got that we hypothesize that the mean difference is 0. So we'll always have a 0 there. Tell it that you got labels, choose your alpha, and then your output. So this is what we get. There's our sample mean for the young, sample mean for the old. So that's talking about math 30 marks. The variance, of course, are s squared. Here's your n's. Here's that pooled variance there. That was the p squared there. And here's our t star, which we calculated. And then we're comparing that to 1.984. And up here, I think we had 1.99. And, and that was just because of the t-table. You had to actually round go to the nearest one there. That's why they're just a little bit different here. But what we end up here then is not rejecting HO. And if you take a look at the p-value, this p-value here is 13.6 is actually greater than an alpha of 0.05, and so you do not reject HO. So that's how we deal with the test and confidence interval for differences of means where the variances are unknown but equal. Now what we're going to do is take a look at tests and confidence interval for the differences of means, independent samples, population variances unknown, so it means that we're going to be using a t-test, but unequal. So this is the most common type of problem that we're going to be encountering here. And so again, what you could do is you could, if the two variables are already in two separate columns, you could stick them into the ANOVA template, or of course you can unstack them if you've got a nominal variable and a interval variable, and then unstack them according to the two classifications of the nominal variable, so you have two different columns, and then stick them in there, check your normality using the Anderson-Darling test, and then you can check the Bartlett's test for homogeneity of variances. And if that fails, then we've got unequal variances. And so we should be using this formula down here. So we're not using a pooled standard deviation. We're using a formula that actually looks really similar to that very first test that we did, where we used a Z. So Z star is equal to x1 bar minus x2 bar, etc. And then in the denominator, we had sigma squares instead of S squares. Now, where it becomes goofy, though, is the degrees of freedom. This is the symbol nu for degrees of freedom, and isn't that a horrible looking thing there? That's how you calculate the degrees of freedom there. And that's why I'm not going to get you to do this by hand on an exam here. I just want you to be able to do this by computer here and using Excel. So that's all I want you to note here. So it actually doesn't follow a t-distribution or a z-distribution, but we can approximate it with a t-distribution by figuring out the degrees of freedom this way. So it's really goofy. So let me give you an example down here. Oh, sorry, down here. This is your confidence interval where this is just your degrees of freedom, that nu. So consider the Stats 101 data set used in class. And by the way, you can go and try all of these yourself because you've got access to that data set in your supplementary files folder. So is there a difference between the average age, all right, so that's an interval variable, of students with brown eyes versus those with non-brown eyes? So that is a nominal variable. And so we're going to have brown-eyed students, and then we're going to have their different ages here, and then we're going to have the non-brown-eyed students and their different ages here. And so that looks like a good candidate there for ANOVA, except that with ANOVA, you've got to have equal variances. And so if you don't have equal variances, then you need to use the t-test with unequal variances. So that's what this test is about here. So let's take a look down here. And again, this is just really informational. You're not going to have to do this by hand. But what we've got here is a hypothesis that looks really similar to what we would have, of course, in an ANOVA problem, right? The mean of brown-eyed people, the mean age of brown-eyed people is equal to the mean age of non-brown-eyed people against the alternative that they're not equal. The t-statistic is this guy down here. And then you need to calculate the degrees of freedom, and this is really where it gets ugly here. So, but I do show you the calculation here if you wanted to go through and try that. So you end up with 65 degrees of freedom. So I wanted to show you this because when you do this on a computer, you'll take a look at the degrees of freedom and say, where did that come from? I don't know how they got that. Well, this is how you get it. Okay, so the degrees of freedom are 65. Back down over here then, what we've got then is a t-distribution with 65 degrees of freedom has a confidence, has critical values of plus or minus 2.0. So we stick that into our T-star formula here, and we get 2.38. 2.38 is greater than 2.0. So we reject HO. We write a concluding statement which says the non-brown-eyed students are significantly older than the brown-eyed students, right? These are the means that we're looking at. So these are the brown-eyed, these are the non-brown-eyed. So the non-brown-eyed students are significantly older by about 4 years on average, it looks like. 3.5 or so. Okay. Confidence interval looks like this. This is just a standard kind of confidence interval where we've got the differences of means. Here's your critical t value used in the confidence interval. Remember that you're using 65 degrees of freedom here, and then we've got these guys here. Okay, so we stick those in, and we get the differences of means is minus 3.44 plus or minus the margin of error of 2.895, and that gives us that the difference between the brown-eyed and the non-brown-eyed students is anywhere from 6.33 years older to about a half year. Sorry, younger. That's a negative value. So brown-eyed students are 6.33 years younger in average, up to minus about half a year, minus 0.55 years younger. So both of these signs are negative. So this interval does not contain 0, and that supports, of course, what we've got up here, where we rejected HO, where they're different. Now, doing this using Excel is pretty simple. All we do is we unstack the variables into the two treatments. And so we've got the ages for the brown-eyed students, and then we've got the ages for non-brown-eyed students. And so here's the brown-eyed students, here's the non-brown-eyed students here. The difference is 0. Tell it you got labels. Defaults to an alpha 5%, which you can change. Give it an output range. Press OK. And do a little dance and you're done, because this is what you get. Here's your means right there. Okay, is that what we had up here? Yeah, I guess it is. Okay. And then here's our sample variances. That's S squared. And then here's our ends. And then this was what we got. We got minus 2.38. And we're comparing that to a critical value here of, looks like it rounds to 2. And so we end up rejecting HO. Of course, your p-value is right here for a two-sided test, right? And that is less than your alpha, and so you're going to reject HO. So there's both the classical approach and the p-value approach. All right, I'm going to look at one more in this particular video here, and again, you're not going to have to do this by hand. And in most projects, we don't actually have this kind of problem too, but if you do run into it, this is how you do it. So this is a confidence interval for the differences of means matched pairs. And that means then that everybody, each respondent then has an X and a Y value. So I think in my introduction, in the first video, I said, for instance, they could be your 306 mark and your 307 mark, and we want to see, are the averages different between the two? So what we do in this particular case then is we use a hypothesis that looks like this. It's just really your standard hypothesis that the means are equal against the alternative that they're not equal. So you could certainly write it that way. Of course, that means that the differences are 0, or this is also how you could write it, is that the difference between the two is equal to 0, the mean of the differences. And the alternative, of course, can be one-sided or two-sided, the usual kind of stuff. This is what the test statistic looks like. It's just a simple t-test, but we have to calculate then the mean of the differences and the standard deviation of the differences. It follows a t-distribution with nd minus 1 degrees of freedom, where nd is the number of pairs. Think of that as the number of respondents. So that's probably what you're talking about here in the type of surveys that you're doing. The number of respondents. Because each respondent, of course, has an X and a Y value, or in the example I said, a 306 mark and a 307 mark. Okay, confidence interval is just a real simple confidence interval, point estimate, margin of error, made up of a t statistic and the standard error of the difference. I've worked through this example here for you, and so let's start down here with down here. And so we would write it this way, that the mean difference is equal to 0 against the alternative that it's not equal to 0, or you could write it, of course, this way. I should go back and actually take a look at this problem here. A survey was made of the Book of the Month Club to see if members spend more time reading than they do perusing social media. So below are the paired sample of 9 members, showing the number of hours spent reading. So here's person number 1. They spend 8 hours reading and 32 hours on social media in a typical week. So you can see they're paired, right, for each respondent here. Assume times are normally distributed. That's still important here. Or is there a mean? Is there a significant difference here? So here's our hypothesis here. Here's our test statistic. Here is your critical value, where your degrees of freedom are n minus 1. So although there is 18 numbers here, there's 9 persons, 9 respondents, so 9 pairs. So it's 9 minus 1 is equal to 8. That gives you critical values of plus and minus 2.306. And then the way that we calculate the differences is just, 8 minus 32 is equal to minus 24. 15 minus 20 is equal to minus 5, and all the way down. Here's the sum. And we can just calculate the mean and standard deviation of this column. So we've got some positives, we've got some negatives here. The mean turns out to be minus 7.778, and the standard deviation is 9.795. And then we stick that into the formula here, and we get a T star. And that T star then is right about here. And so we end up rejecting HO. So it's significantly smaller. One thing I guess I didn't do is write the conclusion here. And what this is showing here then is that because you end up with a negative here, what that's saying here is that the time spent in reading is significantly less than the time spent on social media. Right, and that's because when you calculate the difference, it's negative, and we were calculating reading minus social media. So higher numbers for the social media, and you can see them just looking at those numbers there. All right, let's take a look at the confidence interval. The confidence interval is really easy. We've already calculated this guy here as being the difference of the two. This is the critical value, and then we've calculated these guys before as well. So what we end up here is that, and we're saying then that The amount spent reading is anywhere from about 15 hours to a quarter of an hour less than spent in social media. Now that's a pretty big confidence interval, but we only have 9 people. So if you had 100 or 200 or something like that, you would tighten that up. But the signs are both negative, which would support what we have up here, that there is a significant difference. We reject HO. Now, using Excel, what we do is we use the T-test paired two-sample for means in Excel in the data analysis toolpack. And so you've got, this is your reading scores, and then this is going to be your social media scores. Notice that they have to be the same length, right, because they're paired. So in this case, they both go from F2 to F11. Tell it you got labels, choose your alpha. Down here, of course, the difference is 0 between the two, always. And in all the examples we would be doing. And then here is your output range. So this was what we ended up with. So this actually is useful in that I didn't actually calculate what these means are. But if you calculate the mean for each one here, then what you would end up with is you could sum them up and divide through by 9. And this is what you would end up with then, is 16.889 for reading and 24.667 for social media. And so that difference is about 8, 7 or 8, which is what we had up here. All right. And then we've got the variances. These are just S squared. Their observations, of course, is 9. Pearson correlation is interesting. We'll talk about that later in Unit C, which is the next unit. And here's your T statistic, minus 2.38, which we calculated. We determined that the critical value was plus or minus 2.306, and so we end up rejecting HO. Of course, if we were to do this using a p-value approach, here's your 4%, which is less than an alpha 5%, so therefore we would reject HO. And that is the end of this lesson. There's one more test that we'll take a look at, and that is confidence intervals for differences in proportions, which you may have to do by hand, but I want to show you that in the last video. So let's end the video here. Thanks for watching.